Topic 3.3 Standard Test Methods and Interpretation. From the last topic, we're talking about the concepts of stress and strain, and it is very useful for the standard test methods and interpretation. And within this topic, I will introduce 5 different standard tests which are quite universal. They are tensile test, hardness, fatigue, creep, and impact test. Here, let's start on the first one, tensile test. For specification and design, tensile test is very important to give the engineers ideas how to select appropriate metals for their application and also to select proper metals for their design. And to do the mechanical test, first thing you have to remember, you have to pick up the standard test methods that suit you. And this depends on the criteria from the companies that producing the metal products or the customers who need the standard records of the metal product forms. Right, what do we need for standard test method? We have to have standardized test specimens and the standard test machine. These 2 categories are very important. And first, let's have a look at the test specimen. Here you can see there are 2 different types of test specimen. The first one is the cylindrical rod type specimens, and the second one is the sheet or the plate-like specimens. And this depends on what is the metal product form you received. In the case of you working at a company who's producing extrusion products, and therefore when you do the test, you may have to prepare the specimen which are cylindrically rod shaped. And for those who's working in the company doing metal rolling into slabs and sheets, so the specimen dimensions conform into the plate-like specimen, for example. And you can see that all the dimensions displayed on here is in accordance with the dimensions signified within the standard test method to make sure that the data obtained by the test result will be reliable and valid. And on your right-hand side here is the example of the universal testing machine. It can be either screw-driven or hydraulic. And for this type is the screw-driven machine, as you can see along here. And the test specimen will be gripped along both ends and then carry on testing by moving the screw. And to make it easier, let me introduce you this schematic diagram showing the tension testing machine. As I said before, the specimen is gripped at both ends like this, and with the movement of the screw, we'll move the crosshead down here, and during that time the specimen is said to be tensile loaded, causing the elongation along this gauge length. And when I say gauge length, it is determined on this specimen dimension here. You can see the parallel length, which is the reduced section, but the gauge length is within this dimension. And now back to the test. While specimen is tensile loaded, the load cell attached onto the specimen will report the load experienced by the specimen displayed onto the monitor, and all the load data will be saved relevant to the extension of the specimen. And here we can have several test parameters. Firstly is the load in the unit of Newton, and before the test we have to measure the original area, which is in the unit of meter square. Gauge length in the unit of meter. The stress and strain can be obtained according to these 2 expressions, which is the engineering stress equals P over A naught and engineering strain equals delta L over L naught. And then the stress unit is the Pascal and strain is dimensionless. And for the construction of stress-strain curve, it is obtained from measuring the load and extension while we're doing the test from the start to failure for the calculation of stress and strain. And then we plot the stress and strain relationship as I will show you here. The strain is plotted along the x-axis and the stress, of course, is on the y-axis. And from the expression of the stress and strain, and from the load and extension that we measured at the first place, we can now arrive at the values of stress and strain plotting on this graph, as you can see from these red lines. And I would like to explain each stage of tensile test a little bit in more detail. So please listen carefully. At the first start, when the specimen is pulled by the machine, the metal along the gauge length is uniformly extended. As you can see from here, at the first portion of the graph, it is linear, and that the specimen behaves in an elastic manner, where the stress is proportional to the strain, giving the linear portion of the curve. And this will come within a few seconds, and then the curve approaching yielding stage and work hardening or strain hardening until the stress reaching the maximum. And you can see that the gauge length of the specimen is still extended uniformly till reaching the maximum point of the stress, and this point is very important. It's normally called ultimate tensile strength and giving the level of the maximum strength that the metal can bear without failure. And beyond this point, the deformation is not uniform now, as some portion of the specimen here strictly within the gauge length deform locally. We normally call it necking. As you can also see over here that some more deformation is confined within this area and causing this area to reduce in its section more and more until reaching the final stage of fracture. And therefore, for the whole period of testing, we can construct the stress-strain curve like this, which I would like to divide into 6 important steps, which are the first step where the stress and strain are proportional, and it said that the specimen behave in the elastic manner. And next, the specimen will go through yielding, then strain hardening until reaching the maximum point over here that we can obtain the ultimate tensile strength, showing that the specimen can withstand without failure. Then going through necking, non-uniform deformation over here, and that will proceed to the final step of fracture. And next, I would like to demonstrate at each step that qualified on the stress-strain curve. First, if you have a look on your right-hand side here, is a copper bar gripped by both ends. And while doing tensile testing, we are recording the stress in the unit of megapascal and displacement or delta L in the unit of millimeter. And here we go at the first step, just a small portion of the elastic relationship of the stress and displacement. As the test continues, you can see that the length of the sample is elongated uniformly, and that is the stress is proportional to the strain or displacement. And after that, specimen getting through yielding and strain hardening to approach the maximum stress level up here. The deformation is still uniform along the length, but reduced in the cross-sectional area. And beyond the maximum point, the specimen will experience necking that's taking place over here. It is not necessary that necking will take place exactly at the middle of the gauge length. It can take place anywhere along the gauge length here. Once it happened, the deformation is not uniform anymore, and this reduced section will lead to the final fracture exactly where the specimen neck. And so we have fracture, as you can see incidentally on the stress and displacement curve as well. So from the test, I would like to summarize specimen behavior during tensile test. Here again, we have the stress and strain on y and x axis, and the red curves here showing the stress-strain relationship or the flow curve at different stages. Here I give you the example of the specimen dimensions. Before we doing the test, we have to measure all the gauge length and also the area the tensile force acting on. So the gauge length is defined as L0, and the area of the specimen before doing the test is defined as A0. And we use this dimension for the calculation of stress and strain as we measuring the load and delta L. Remember that when we calculate the stress is related to the load at each step of loading, but always based on the original dimension. And here, the stress is the load that always based on A0. Same here again for the strain. The strain at each step of the test can be calculated from delta L, but always have to be based on the original dimension, which is L0, that I will show you later on. Here, when we're starting from the original dimension of specimen, once we're loading, the stress and strain is in linear relationship. Then the gauge length of the specimen is extended uniformly, as you can see here. This behavior is said to be elastic, and if you recognize the area under this curve is a triangle, and it shows the energy that required to deform this metal in this stage. Actually, for metal, this area is very small and takes just few seconds. But from this graph, I would like to exaggerate this area a little bit because we need some discussion here. And if we look carefully on this triangle, we can see that the strain down here is the elastic strain that is caused by pulling the sample up to the elastic limit here. And so the elastic limit is the last point on this linear graph that the stress is still proportional to the strain. In this region, we can obtain one important parameter, which is the Young modulus that can be calculated from the slope of this curve or the values of the stress over strain. And beyond the elastic limit, we're going through the yielding step. The metal piece experiences plastic deformation and undergone strain hardening till reaching the ultimate tensile strength here. After this point, necking taking place, as you can see that the reduced section of the cross-sectional area confined to the location along the gauge length of the specimen, and that will lead to fracture, and that is the end of the test. And now let's analyze a little bit on the areas under this graph beyond elastic limit. This area shows the energy consumed by the specimen during strain hardening and necking through fracture. And this area is huge for metal. It means that metal can be deformed into a range of deformation, giving a variety of shapes. And within this area, see carefully from this line from the maximum point. The areas to the left showing uniform plastic deformation, and the areas from the right-hand side shows non-uniform plastic deformation. As you can see from necking, that deformation is confined at some local area, not throughout the gauge length, hence it is non-uniform. And then, if we talk about the strain, we have this bit for elastic strain, and the rest is the plastic strain. So the total strain is the summation of the elastic and plastic strain. For summary, we're starting from the specimen prior to the test with the original dimension of L0 and A0. Then, once it extends to the elastic limit, the specimen extended along the gauge length uniformly beyond elastic limit and yielding till reaching the maximum point where specimen bearing the highest stress level. Beyond this, necking taking place, and then the deformation is not uniform anymore. It is confined in the necking area till reaching the fracture stage over here. Right, this is how specimen experience tensile loading till fracture. So next, let's have a look at some parameters that we can get from testing specimen under tensile. First, when we're looking on the first bit of the graph, which is the linear portion, we can calculate, as I said before, the modulus of elasticity or the Young's modulus. The definition of Young's modulus is a measure of material stiffness up to the elastic limit, giving capital E as the symbol. And within this elastic region, the stress is proportional to the strain following the Hooke's law. As you can see from a linear portion of the stress-strain graph here, when loading, the stress is proportional to the strain, giving the slope of the modulus of elasticity, or the Young modulus expressed by this equation, which is the stress over strain. But when we unloading the sample, the material can change into its original shape. It means this elastic behavior is recoverable. Some engineers unfortunately ignore these properties, but I will tell you that this property is quite significant. For example, for the application where the plastic deformation is not allowed, imagine when you use this steel beam or steel wire rope. You can't take a chance that yielding will occur in service, so you need this steel wire rope or the steel bar like this behave in the elastic manner only, so you don't give any deflections from the whole structure. Imagine that, how safe it is. imagine that if you are a civil engineer, you have to select the metal. And these parameters you have to consider for structural materials as well. And next, when you look at in the areas of sports, here comes golfing, and you need elastic property of the golf clubs here. And next, for biomedical or the implants, this is the example of hip joint. You wouldn't want to use the hip joint like this as an implant in your body with too small modulus with you. And the next step of tensile test, beyond the elastic limit, as I said before, which is defined as the greatest stress that the metal can withstand without undergoing plastic deformation. So, beyond this point, the stress and strain curve deviates from its linear portion. At yielding, the yield stress is defined as the stress that produces a small amount of strain equal to 0.002. Or you can see from the expression here that the 0.2% yield stress is the load at yielding, or Py over A naught. And how can we find load at yielding, or Py? Remember when we said that is the stress defined at the amount of strain equal 0.2%. So over here, at 0.2% strain, that is equal to 0.2 over 100. So we arrive at the strain of 0.002, which is over here. And then, to find the load at yielding, we drawing a line parallel to the first line, which is having the same slope, and crossing the blue line at load of yielding, or Py, like this. And the significance of the yield strain comes to twofold, both to the design on the onset of yielding. First, on the structural integrity. If you're an engineer, and imagine when you have to choose materials from specification, you have to make sure that you will keep this structure safe for working in service. And that's why we have to know the yielding point of the metal. And another aspect is in the area of metal forming. And when you want to deform the metal to desirable shapes, it means that you have to put the load beyond the yielding so that the metal can be deformed into any kind of shape that you want. And because when we apply the load below the yield point, we can't do the metal working operation. So this is how metal yielding is important. And next, beyond the elastic limit and yielding, the material is permanently deformed or material has undergone plastic deformation. And if we load the metal piece over here up to D, remember the area under the graph showing two types of deformation. One is elastic deformation and another is plastic deformation. So at point D, the metal piece experienced firstly elastic and then undergone plastic deformation. And from this point, let's think a little bit carefully. Upon unloading, the graph will come down following this linear portion, and the metal is elastically recovered by the amount of elastic strain, that is the area within this triangle. This amount of elastic strain that is recoverable is significant for metal forming operation, as I will show you here. It means if you extend, for example, if you extend the specimen from its original length from 30 millimeters, for example, when we loading up to D, the gauge length extended up to 40 millimeters, for example, and once we unloading the sample, finally we have the specimen gauge length reduced down to 35 millimeters, and that means 5 millimeters of extension has been recovered by the elastic strain. It means when we extend the metal piece to 40 millimeters, on unloading we will get just 35 millimeters long, and that's gonna get into some problem while we working on metal operation. Here is the significance of the recoverable elastic strain. If you have a look at this metal operation, which we will form a cup by drawing operation. First, we place the metal piece on the top of the die, and we here have the punch. On the operation, the punch will move down and draw the metal piece into the mold. And that's exactly what happened to the metal that has been loaded up to D. And once we remove the punch, it is the same as we unloading the sample. the wall of the cup spring back a little as a result of the elastic recoverable strain. And this might make the cup not in the desirable shape as the customer wants. So on the metal operation, you need to take the recoverable elastic strain into consideration. Trial and errors and simulation may need to correct these errors. And next, at the ultimate tensile strength, you see that after yielding, material experience strain hardening while approaching the maximum strength, where it can withstand the maximum load just before experiencing necking. And over here, the ultimate tensile strength can be defined by the maximum load over original area or not, as you can see from this expression. And the significance of the ultimate tensile strength is when we consider on load-bearing performance, working stress, and material specifications. And if engineer consider the working stress based on the maximum tensile stress, we normally use a safety factor. It means that if the specimen tested to have the maximum tensile strength of, for example, 500 megapascals, you wouldn't want to use this material at this level of strain because it's too risky to go fracture. So we have to apply the concept of working stress, which is the maximum tensile strength divided by some safety factor. And if the safety factor is 2 in this case, so we can come out with the working stress at 250 megapascal only for this steel to be used in service. And that will make people safe based on this consideration. And finally, we arrived at fracture strength. And therefore, after necking, materials undergo non-uniform plastic deformation with reducing area subject to loading. And here we come, the fracture strength defined by the fracture load over the original area, as you can see from this expression. And the significance of the fracture strength is the consideration on prevention against failure. So overall, we have the strength at different stages of tensile loading. First the yield strength, then the maximum strength, and the fracture strength. What kind of stress level you want to find, you just find the load at that stage divided by A0. And that's for the strength. Now let's move on to ductility, which is a very important parameter showing the safety of the metals and ability of metal to be formed. We have 2 parameters over here. The first one is percent elongation or percent E. It is defined as the amount of extensions of an object under stress, which is expressed as a percentage of the original length. And next is the reduction of area. And this is how we're talking about the strain. From the picture, you can see this point showing the original gauge length or L0. And once it's extended to the final gauge length or LF, the difference of these two divided by the original area times 100 will give you percent elongation. Another parameter is percent reduction of area or percent RA. It is defined as the proportional reduction of the cross-sectional area of a tensile test piece at the plane of the fracture measured after fracture. So to make it sound easy, let's have a look onto the equation. For the elongation is similar to the strain times 100. So therefore, you have the original gauge length here and the final gauge length here. The difference of these values over L0 times 100 is percent elongation. And for the reduction of area, it means that you have to first measure the original area or A0. And then after the test, you have to measure the final cross-sectional area. And the difference of these two values over the L0 times 100 will give you percent reduction of area. And normally in terms of engineering, we apply percent elongation for the ductility of metal. Other parameters that I will explain a little bit more based on the area under the curve, or it shows that how much the energy consumed during elastic and plastic deformation. First, remember the area under the triangle here shows the elastic behavior of the metal, and this area is very small in reality. The elastic behavior shows the input energy that is restored as the elastic energy and within this area, and it is released after unloading. and that showed you earlier about recoverable elastic strain. The area under the curve is called resilience, or UR, from this expression that is equal 1/2 stress times strain. It looks like the area of the triangle here, with the strain as the base of the triangle and the stress as the height of this triangle. Beyond this point, over this area, that's the metal experience plastic deformation. Here the plastic behavior that the input energy is restored as the plastic strain energy and is not recoverable. It is permanently used to change the metal shape. And next is the toughness parameter. As I said before, the toughness is comparative to strength plus ductility. As you can see on the whole area of the stress-strain curve, the toughness is defined as the whole area under the curve, showing the all energy used during elastic and plastic deformation. If the metal has high toughness, the metal has high ability to resist crack propagation to it. And 3 expressions here are given for the definition of toughness in terms of mathematical expression. And for ductile materials, these 2 equations are used that you can have the toughness as the maximum strength times the fracture strength, or you can average both yield stress and maximum tensile stress value first and then times the fracture strength. And remember, the more area under the curve showing the higher toughness of the materials. This slide will compare different behavior between brittle and ductile materials. If you have a look first on this stress-strain curve, starting from A to B, showing brittle material behavior, and you can compare the area under the curve is much smaller than another one that is ductile, starting from A through B prime. And when you look at these fracture surfaces, these first 2 sample halves after the test showing very brittle surface, and this means the samples consume very few energy during fracture. And on your right hand side here, these 2 sample halves after testing giving reduced section over here and a lot of plastic deformation going on during fracture. And this will give the example of the metal has been tasted and giving the graph of ductile metals like this. And here's on your right hand side showing the example of metals with different properties. First, if you look at this graph of high carbon spring steel, it shows there more energy that this carbon spring steel consumes within its elastic behavior, and that's why it's used as a spring. And for structural steels, huge area of plastic deformation over here, and that is good for this steel to be easily deformed to make various shapes and sizes for construction. Now I will come to the summary of unit actual tension test. First, over here, in tension test, specimen is subject to axial tensile loading until fracture. Load and extension are measured and expressed as the stress and strain, as you can see from this graph. The initial linear portion of the curve is the elastic region following Hooke's law. At point A is the elastic limit, and that's the greatest stress that metal can withstand without undergoing plastic deformation. And the slope of the curve is the Young modulus. At point B is the yield strength, defined as the stress to produce a small amount of strain equal to 0.002. At D, as the plastic deformation increases, the metal becomes stronger until reaching the maximum load, giving the ultimate tensile strength. Beyond D, necking takes place and the load drops to failure, as you can see from the final specimen fracture over here. The elastic strain is recognized from here, and therefore the rest is the plastic strain. The total strain is the summary of the elastic and the plastic strain. And underneath the curve, the first portion here in the triangle area shows elastic deformation or elastic strain energy. And beyond the elastic limit, we have plastic deformation behavior going on over here. To the left of the maximum strain, it is uniform plastic deformation. But to the right, it is non-uniform plastic deformation.